I'm Chen. I'm from Oak Ridge, and I'm going to talk about our recent work on the numerical modeling of the friction stir welding. And the title of my presentation is Development and Applications of the Multi-Physics Coupled Numerical Model for Friction Stir Welding. This is the co-authors, Zili Feng at Oak Ridge and Qingyu Shi from Tsinghua University, China. I divided my presentation into three parts. The first part is modeling. I will give a brief introduction to this modeling of the material behavior in friction stir welding. In the second part, I will introduce our numerical model, and the third part will spend on introducing some applications of our newly developed model. So the friction stir welding is solid steel joining. And during the welding process, large heat was generated and the significant material flow occurs. So the weld formed as a result of thermomechanical processing. So in the modeling of the friction stir welding, the temperature field and the material flow field has been recognized as the key point for the modeling. In order to model the temperature field and the material flow field, we need first we need a heat generation model. The heat generation during friction stir welding is based on the heat was generated in friction stir welding from the friction and the plastic deformation. These two heat generation mechanism is related to the material flow field. And regarding the interplays between the interfacial friction between the friction stir tool and the workpiece, between the friction and the material flow, and regarding these constitutive relationships between the temperature and the flow stress, we recognize that the multi-physics phenomenon is involved in friction stir welding. In the previous model, researchers are on the way to building up this multi-physics coupled models to capture the material flow during material behaviors during friction stir welding. And the more we captured this interplay between these phenomena, the more application we can find for the developed numerical model. I'm not going to cover everything today, and I will focus on the interfacial friction between the tool and the workpiece today. The interfacial friction between friction stir tool and the workpiece is very important. It's critical for modeling the material behavior during friction stir welding, as it will determine the heat generation, and it will plays a very important role in determining the material flow field. Actually, it provides the driving force for the material flow. So the friction in the between the tool and the workpiece will determine whether the material will follow the motion of the friction stir tool. So we focus on the interfacial friction in this study. From the point of view of the governing equation, the interfacial friction is also important. We need this energy equation and the momentum equation and mass conservation equation to simulate the temperature and the material flow during friction stir welding. The interfacial friction provide critical boundary conditions for this equations. So in the previous researches, the interfacial friction between frictional tool and workpiece has been recognized as a very important point. So they use this this equation to define the boundary condition on the tool workpiece interface. This equation describes the material velocity at the interface. So actually, there are totally three kind of boundary conditions they used in the researches. The first one is the pure sliding condition, where the material at the interface is defined to be zero. So actually the material flow is ignored. And another one is the sticking condition, where this variable delta is defined to be 1. So the material is assumed to be moving at the same velocity with the tool at the interface. And another one is the partially sticking sliding condition, and where there's a condition between the pure sliding and the sticking. So this variable delta is between 1 and 0. So I will give a brief review on these three boundary conditions. The first is the pure sliding boundary condition. So the pure sliding condition, it is usually used in the early thermal models. So the material is actually ignored in these models. This boundary condition is not quite true. So as we know that we have significant material flow during friction stir welding. The second one is the sticking. So in the sticking condition, people assume the material at the interface is moving at the same speed with the friction stir tool. With this condition, people has proved that excessive material flow is included if we use this boundary condition. So the plastic deformation zone is over-predicted. So it is very important to include the interfacial sliding between the tool and the workpiece. This is the values of the delta variable people use in their works. It is recognized as a very important parameter in determining the heat generation, the material flow in the research to determine this variable. So it is very, very important to determine the extent of sliding between the tool and the workpiece. So in this research, we are developing a new frictional boundary condition. And based on this boundary condition, we developed a numerical model for capturing the material behavior during friction stir welding. After this, we identified the influence of the interfacial friction on the temperature and the material flow. We also explored the potential applications of the model in predicting the friction-induced phenomena during friction stir welding. So that's the second part, our numerical model. We developed this new frictional boundary condition based on this consideration. We allowed the dynamic sliding between the moving tool and the workpiece. We use these equations to determine the magnitude of the frictional stress and the direction of the frictional stress on the interface. So the magnitude of the stress is based on the Coulomb friction law. Is dependent on the frictional coefficient and the contact pressure on the interface, and the direction of the shear stress is the same as the relative velocity. The relative velocity is the difference between the tool velocity and the material velocity in this equation. By using this equation to determine the shear stress at the tool workpiece interface, we allowed the dynamic sliding between the tool and the workpiece. For example, if the material velocity is very low, like this, it's nearly a pure sliding condition, the shear stress on the shear stress on at the interface is definitely the mu p is determined from the frictional coefficient and the pressure. If the material flows in a faster speed, so the relative velocity becomes smaller, but the magnitude of the frictional stress is not it does not change. If the material flows at the same velocity with the tool, the shear stress will, this is the sticking condition, so the shear stress will take this value, and if the material flow even faster than the tool, the frictional stress will change its direction, so it will act as opposite direction as the material flow. So when the material velocity is close to the tool velocity, there is a transition from there's a very sharp transition from the positive force to the negative force. So here we include one another smooth function to deal with this to deal with the singularity in the force induced by this sharp transition. On one hand, this sharp change will cause numerical difficulty in we obtain a sound numerical solution. On the other hand, we here introduce velocity dependent frictional stress to this model. It is so in this when the material velocity is close to the tool velocity, so will be changes in in the magnitude of the shear stress. We use this smooth function to add this modification to the equations. So this is the boundary condition, and this is the heat generation model. In this heat generation model, we assume that the heat is generated from the frictional heat friction and the plastic deformation. Heat generated from the friction is dependent on the frictional stress and the relative velocity. The heat generated from the plastic deformation depends on the flow stress and the strain rate. So I give several brief explanation. When the material velocity is very slow, the heat, almost all the heat should be generated from the heat friction, as the material, the relative velocity is almost the tool velocity. When the material velocity increase, so the relative velocity between the tool and the material and the workpiece will become smaller. So the frictional heating becomes decrease, and there should be much more plastic deformation. So much more heat was generated from the plastic deformation. When the material velocity is almost the tool velocity, so the relative velocity is very small. So the almost all the heat was generated from the plastic deformation. So this is the based on this physical models, we established this three-dimensional model based on the computational fluid dynamics. This is the geometric model. In this model, the material flows into this fluid zone at welding velocity, and the material will interact with the tool with all the frictions and heatings here in the tool workpiece interface, and the material will flow out of the fluid zone from the material outlet here. In the model, we use temperature-dependent thermophysical properties and the flow stress model dependent on the temperature and the strain rate. Let's see some simulation results. First, we do systematically study on how the frictional coefficient will influence the material behavior. This is the heat generation rate. We can see that with the increase of the frictional coefficient, the total heat generation rate increase, and when the frictional coefficient is relatively low, the material this is the total heat generation, and this three picture shows if you see the counter plots, it shows the volumetric heat flux due to the plastic deformation, and these vectors on the interface, it shows the heat flux due to the friction. With the increase of the frictional coefficient, the much more material flow is simulated. So the heat flux due to the plastic deformation increase. When the plastic deformation, when the frictional coefficient is very small, almost all heat is generated from the friction. With the increase of the frictional coefficient, the role of the plastic formation on the heat generation become more significant. This is the temperature field we from the different frictional coefficient. The temperature field is significantly influenced by the frictional coefficient. But we compared this predicted temperature history to our experimental data. The comparison shows the frictional coefficient is close to 0.2. This is the predicted velocity distribution under the tool. We can see that the deformation zone is enlarged by the frictional coefficient. This is, if we compare the deformation zone shape to the stir-down shape in the weld, in the microstructure of the weld, we can see that the shape of the deformation zone, the predicted shape of deformation zone is closest to the from the frictional coefficient is when the frictional coefficient is 0.2, it is agrees best with the microstructure of the weld. So comparison between this deformation zone and the microstructure and the thermal history could help us to determine the proper frictional condition during the simulation. And in the third part, based on the developed model, I want to show the potential application of the model on prediction of defects formation. First, this slide shows how the tool rotating rate will affect the deformation zone. So this is using our model, we predicted the velocity distribution under the tool with different tool rotating rate. By comparing the predicted velocity profile to the microstructure, the experimental microstructure result, we can see that the size of the deformation zone is increased significantly by the tool rotating rate. In higher tool rotating rate, we have a much larger stir zone. Okay, thank you. So now we will. I need to speed up. So in this wells, it is the welding parameter is 500 RPM and 40 millimeter per minute. So we can see defects here. We want to determine a proper defect criteria for the prediction of the defects. So we analyzed the material flow pattern in these two planes. One plane is the 1 millimeter away from the shoulder, and another is 2 millimeter away from the shoulder. From the upper plane, we can see the material velocity. The predict material velocity is like this. In the very vicinity of the pin, we can find the material is flowing around the pin in a continuous rotating band. In this case, there's no defects formed. But in the lower plane, when we see the material flow pattern, we can see there's also a rotating zone, rotating band around the pin, but the band is not continuous. So if we recognize this as a defect criteria for predicting the defects, so we expect the defects criteria is the defects forms at the position when this transformation band is not continuous. We use this criteria to analyze the welding condition in the 500 RPM and 40 millimeter per minute. So we determine the discontinuity of the rotating band occurs in this area. So the position is consistent with the defects position. And so if we change the welding parameters, we found that in the high, with constant welding speed in the high rotating speed area, there's no there are no defects, and if we reduce the RPM, the defects will appear on the advancing side. We compared our predicted parameter window to the experimental parameter window. If we take the welding speed as 40 millimeter per minute, it's the predict trends agrees well with the experimental trends. So in summary, we developed a new model, and we recognized the simulated temperature and the material flow is sensitive to the frictional condition. And we proposed a method to predict potential defects from our development model. Thank you.